So, Bobby, when we talked about GMR, we talked about a multi-layer stack, right?
Yeah.
Two ferromagnetic separated by a conducting layer, and you repeat that.
Yes.
Right. But we also saw that the graph for this is
Symmetry.
Yeah, symmetric.
Yeah.
So, I mean, there's some linearity here and linearity here,
Yeah.
but the value you get is the same here and here.
Correct.
Right? Whatever value you get the same value here. Now, if you want some linearity, proper linearity,
for the change in resistance.
for the change in resistance,
with respect to magnetic field.
yes. One of the ways of doing that is by the structure that you see here. So here,
What is the structure?
so this structure, so you have, let's say, a substrate.
Yeah.
Or let's say a silicon substrate or
Yeah.
semiconductor. And you deposit a free layer. Okay. Let's say you deposit two ferromagnetic layers.
Yeah, stands for ferromagnetic.
Ferromagnetic, right? Let's say you deposit a ferromagnetic layer, then you have a non-conducting layer.
Yeah.
Non-magnetic layer.
Yeah.
Another layer, and what you call an anti-ferromagnetic layer. Now, what's happening here? So, this is a little bit different to the traditional GMR stack because you can get similar results for a much smaller stack. So, what we do here, and there's a lot of, and there's more linearity compared to a GMR stack.
So, what bottom three parts, layers, look similar to earlier one?
Yes. So, yes. So, what we do here is, so what happened before? We had a ferromagnetic layer and it changed its magnetization according to the applied magnetic field.
Yeah.
Same here.
Yeah.
Then you have your non-magnetic layer.
Yeah.
Points. Same. But this third layer that you have
the
here,
top layer,
we actually pin the magnetization in one direction.
Pin means
you fix it so that even if you apply a magnetic field, it will not change.
What is that we are pinning? Pin?
We are pinning the magnetization of that
layer above.
Yes, the layer above. It can be the other way around too, but the whole idea is this.
Okay.
So, but how do we do this? Right? So, one of the things is that if you want this to remain in one direction and this one free to move, right? And so, what we do is you probably heard of an antiferromagnet.
Yeah.
Okay. Let's say let's take this example here. You have your ferromagnet, right? And you have, let's say it's kind of biased towards one direction. Okay.
This is one layer.
Yeah, this is, let's say, this layer.
Okay.
Now, let's say you have an antiferromagnetic layer, right? But let's say it's at a temperature where it's not ordered. Okay. So,
it is random.
It is random.
Okay.
Okay. So, it could go in different directions, for example. Now, when you apply a magnetic field, let's say you apply a magnetic field in this direction, what's going to happen to this? Obviously, these ones are going to be in that direction.
Yeah.
Right? Because it's a ferromagnetic layer.
Correct.
Okay.
So it just remains in that direction.
Yes. This antiferromagnetic layer is going to
align, is it?
Align, but in an antiferromagnetic way. So antiferromagnetic means this way, no? Yeah, this way and this way. Like that.
Okay.
Right? So that in an antiferromagnet, your neighboring domains are aligned opposite to each other. Like this. But
within the layer, they are aligned like this.
Yes. So this is your...
So that means your resultant is nothing.
Yes. Your total magnetic moment is 0. But
initially they were random.
Yes.
When you applied some magnetic field, they align like this.
Yes. Which is called antiferromagnet. I mean, same as let's say a ferromagnet, or let's say a soft ferromagnet. If before you apply a magnetic field, they won't be aligned perfectly.
Yeah.
Right.
So when you applied a magnetic field, the upspin and downspin are aligned kind of like this.
Yes. Then, right, if you cool it, I mean, I don't want to get into too many details, but just for the students to understand how this works, if you cool it to a certain temperature,
It remains like that.
it remains like this. And
What is that?
there is some interaction going on
Between these two.
Yes, at the interface,
Mm-hmm.
right? Which is called exchange bias. I mean, interested students can have a look at that. Bias means it's biased in one direction, right? So in this case, when you cool it to a certain temperature, you apply magnetic field, you cool it to a certain temperature, this direction will be fixed. And the antiferromagnet helps it to remain in that direction, even if you apply a magnetic field now in this direction.
Okay. That's where this pinning is.
That's why the term pinning comes from. It's pinned in one direction, whereas this one is free to move. Okay. So this is what we call a spin valve type GMR sensor. Now, this if you look at the graph for this one, okay, generally we have the free layer and the pin layer in a 90-degree angle, which is what you see here.
90-degree angle?
Yes. So this one is, so the top one, as you saw before, is fixed, right?
Yeah.
So it's fixed everywhere.
Yeah.
This one is either coming out.
I
think dot is coming out. No?
Yes.
Yes. So this is now out.
Yeah.
So it's at a 90-degree angle.
Out of the plane.
Yeah. So if you look at this X and Y, I guess if you look at the stack from the top and if you can see through, then you'll see one layer will be, your pin layer will be in this direction.
Okay.
Right? 90 degrees to X. And your free layer is free to move
in that way.
And there's an angle called theta F between the free layer and the pin layer. But initially, it's pinned perpendicularly.
Okay.
So when this happens, if you apply magnetic field in this direction, right, this layer will now change to this direction. Okay. Now you have a parallel arrangement.
Yeah.
Similarly, if you apply magnetic field in the opposite direction, they will be antiparallel. And you get this nice kind of graph here. There you get a very nice linear range here, which we do not exactly see
in the previous one.
Plus, you don't need a huge magnetic field
to do this,
to change the spin. Whereas for the stack, sometimes your saturation fields are much, much higher.
Oh, then is it more sensitive compared to the previous version?
So spin valve sensor is generally more sensitive to magnetic fields. Now, if you look at the resistance, it will be R0 plus theta F. Now, that's the angle we show here, divided by 2. Now, we already know what this is, right? This is R antiparallel minus R parallel. So maximum change, right? Which is what you see here, R peak, RA peak, the maximum change. R0 then is what? RP plus del R max divided by 2, because it's halfway right here. Okay. So with this, you don't also have to wait for all the ferromagnetic layers in a multi-stack to change directions. Here you have a much smaller stack, and this magnetic fields you need to apply to change this is much smaller. So it's very kind of sensitive device compared to coordinate GMR.